Hi everyone, in this video we're going to learn how to compute work for stretching or compressing a spring, and part of that will be learning Hooke's law. Let me remind you that to compute work when the acting force is varying or changing, we have to use the definite integral. So W represents work, f of x is the function representing varying force, and the limits of integration a and b define displacement. So it's from a to b. In other words, object is being moved by this varying force from position A to position B. One example of varying force is when we apply that force to either stretching or compressing a spring. Because according to Hooke's law, the force needed to stretch or compress a spring by some distance beyond its natural length is proportional to that distance. And this is just a general description of that law. But let's highlight key words to better understand what that law says. Okay, so it says that force needed to stretch or compress a spring by some distance beyond its natural length is proportional to that distance. And what it means, so basically what it means is that further away I'm going to stretch or compress the spring, more force needs to be applied. Well, that means that to find work required to stretch or compress a spring will be calculated by this definite integral, right? Since force is varying. So now let's talk about the force function for springs, and that's going to be part of Hooke's law. So Hooke's law states that the force required to maintain a spring stretched or compressed x meters beyond its natural length is proportional to x, provided that x is not too large. And here's the force function, so f of x equals k times x, where k is the positive constant called the spring constant. Let's try to understand what all this means. First of all, let's look at everything involved in that force function f of x. So k is spring constant. So spring constant is a certain characteristic of a spring, and in simple words, it basically measures how stiff or soft a given spring. And it should make sense that for stiffer spring, more force required to stretch it or compress it. And then x represents displacement from to, so in other words, well, we stretch spring from this position to that position. And we're going to talk about how we describe positions in a minute. But let me go back to the beginning of the Hooke's law. What else is important to note is that x, the displacement, is measured in meters. And then it says x meters beyond its natural length. So what is the natural length of a spring? So the natural length of a spring can be measured when it's in the resting position. In other words, when either stretching or compressing it. It's also called equilibrium, and it's shown here. So when no forces are acting on the spring, it's considered to be an equilibrium. And while each spring will have its own natural length, the way we're going to think about it is the following. So we're going to imagine that every spring is sitting along the x-axis. And where that spring ends in its resting or equilibrium state, at that place, x equals 0. So once again, think about that line as the number line. It's like x-axis. So that's where we have x equals 0 on that number line. Now when we stretch a spring, we pull it further to the right. And that means that x values are starting to increase in a positive direction. So notice that here for this new position of the spring, or I should say where it ends now, x value is positive. So if we had to describe the displacement, we would say that displacement in this case is from x equals 0 to x equals 1 meter, 2 meters, whatever it is. And what else we show on this picture is that f, which is force, is greater than 0. Now I need to make a note there are a few versions of Hooke's law, in particular how the force function is written. So the way we have defined it here, this force, again, it represents force required to stretch the spring or compress the spring. So for this reason, this force is acting in the same direction as we're stretching the spring, right? Sometimes Hooke's law is defined in terms of the restoring force of the spring. That means that it's going to be force of the spring itself. And we of course know that when we're trying to stretch a spring, it's pulling back, and that's what we call restoring force of the spring. And that force has always opposite direction. But once again, when we have here on this screen, we're talking about force required or needed to stretch the spring. So it's in the same direction in which we are pulling the spring. So in this case, force is positive. Now, when we try to compress the spring, what happens is that the end of the spring from its equilibrium position gets moved to the left. Now, and if right here we have x equals 0 on the number line, then as we compress the spring, its end will be at some negative x value. And since F represents force required to maintain a spring compressed, its sign is consistent with the direction of the movement of the spring. So this is how we view stretching and compressing of a spring. A couple more notes from Hooke's law. Notice that it says, provided that x is not too large. Well, x is the displacement. Well, you probably know from your own experience what happens to a spring if you stretch it too much or if you compress it too much. Then it's not going to come back to its equilibrium state. And that's why we do have this note in Hooke's law that all this works provided that x is not too large and spring can return to its natural state. And then finally, one more comment about K, spring constant. Well, it's a positive constant, and that's the one that determines how the force required to stretch or compress spring is proportional to the distance by which it's going to be stretched or compressed. Let's look at an example. In this example, it says that spring has a natural length of 40 centimeters. If a 60 Newton force is required to keep the spring stretched 10 centimeters, how much work is required to stretch the spring from 45 centimeters to 50 centimeters? So let's start by making a sketch. Let's say that this is a spring, and we know that its natural length is 40 centimeters. Well, we also learned that the natural length of a spring corresponds to x equals 0 along this horizontal axis. Next, it says that if a 60 Newton force is required to keep the spring stretched 10 centimeters, how much work is required to stretch the spring from 45 to 50 centimeters? Well, obviously we're asked to find work. Well, that means that we'll have to set up and evaluate integral that has this form, integral from a to b, and that will describe the displacement of f of x dx. Well, where f of x, force function. Now, the problem is that we're not given a force function, but we also just learned that by Hooke's law, force required to stretch a spring x units or x meters is proportional to that distance, and it's proportional to the spring constant. So that's going to be the function that we'll have to integrate. But now K is the spring constant. Where do we get it? If I start reading the second sentence, it says that a 60 Newton force is required to keep the spring stretched 10 centimeters. Notice that we're given force, and we're also given, well, 10 centimeters. That's the displacement, so that's x. In other words, we're given the specific value of F, force, and we're given specific value of the displacement. And since we know those two, we should be able to find the spring constants. I'm going to take 60 newtons, 60, and set that equal to K times displacement. Well, we're given 10 centimeters. But remember that in the Hooke's law, it said that displacement x should be expressed by meters. So that means that first I have to convert it to meters. So 10 centimeters is 1/10 of a meter. So it's the same as 0.10, or I can say 0.1 meters, either way. So that means that it's going to be 60 equals K times 0.10. And then from here, as I divide the left and the right side by 0.10, then I find that K equals 600. So the spring constant for this specific spring is 600. And that means that the force function will be f of x equals 600x, right? It's K times x. Well, we found K, 600x. That's the force function. And that's the one that we have to integrate. So let me start setting this up. So to find work, we have to set up the integral. We're going to talk about limits of integration in a second. The force function is 600x dx. Let's think about the limits of integration. That's where we read the second part of the second sentence. It says how much work is required to stretch the spring from 45 centimeters to 50 centimeters. And what's very important to note that the limits of integration, they're x values. What x values? Well, these are the x values from this number line. So we have to figure out what numbers on this number line 45 centimeters and 50 centimeters correspond. Because, look at this, 40 centimeters, which is the natural length of that spring, corresponds to 0, to x equals 0. How about 45 and 50? Let's think about it. So let's say 45 is this far, 45, and 50 is this far. In other words, we're trying to find work needed to stretch spring this distance. And we will find it using the integral. The only thing, let's go back to the limits of integration, right? That's what we're trying to find. What we'll need to do right now is to think to what x values these two positions correspond. Okay, let's think. If at 40 it's x equals 0, what is it at 45? Well, 45 is 5 units further away from 40, so, well, it means that x should correspond to 5 here. So that is x equals 5. But I need to remind myself that it's all given to me in centimeters, so it's 5 centimeters. However, when I start integrating, I should be using meters. So let me just change it right away. So 5 centimeters, it's same as 0.05 meters. And what is the x value at this position? That's where we stretch spring to 50 centimeters, right? If x equals 0 at 40 centimeters, then what is x at 50 centimeters? That's x equals 10. X equals 10 centimeters. Once again, I'm going to convert that to meters, so it's going to be 0.10 meters. Or 0.1. Okay, well, these are the limits of integration. Spring is stretched from x equals 0.05 meters to 0.1. So that's what I'll write here, 0.05 to 0.1. And once you set up this integral, the rest is pretty easy, right? You can see that integration itself will be easy. We can put the constant 600 in the front of the integral sign. X dx. Well, and then antiderivative of x is x squared over 2. And we'll have to evaluate that at 0.1 and 0.05. Okay, so that's 600 times, I'm keeping it outside, 0.1 squared over 2 minus 0.05 squared over 2. So that's 0.005 minus 0.00125. This difference gives me 0.00375. And the final answer is 2.25. And that's work, so it means that units are joules. 2.25 joules. Now, if I summarize this example, then the key steps are making a sketch or drawing a picture to help you determine the displacement. Again, think that spring corresponds to certain values along the x-axis. And second, use Hooke's law to find spring constant and set up the force function. And after that, you just simply have to set up the proper integral where you will be integrating that force function using the appropriate x values that represent the displacement described in the problem.